So a very large endothermic solvation process will be non-spontaneous. So that'll be like oil and water. So our vinegar separates out because the attractive force between water and non-polar oil is extremely small compared to that between water and water. And oil is comparable, actually probably bigger. It'll be the attractive force between oil and oil will be bigger than that between oil and water. So it's a very endothermic process to dissolve oil and water. So it's a non-spontaneous process, and it separates out of solution. If we want to change how fast something dissolves, we have a couple things that we can do. The most obvious one that we tend to do is we stir. So we add sugar to our tea and we stir it. If we don't stir, the sugar will dissolve slowly and will form a high concentration zone around the solid sugar. That will slow the dissolving process. So the sugar will not dissolve well into a saturated sugar solution. And the sugar solution around the sugar will slowly diffuse into the rest of the solution. But if we stir the solution, now we are bringing the high concentrated sugar away from the solid, and we're bringing low concentrated solution in toward the solid. So the rate of dissolving can increase because it's now in contact with unsaturated sugar solution. We can grind the particles into smaller pieces. This will increase the surface area so that the rate of dissolving can be higher. And we can heat the solution. Heating solution does two things. It will tend to increase the rate of dissolving, but it will also tend to increase the solubility of most solids or liquids in solutions. So we have some examples of some soluble substances in water. Their enthalpy of solution, the delta H, and their entropy of solution, the delta S. The entropy is always positive, but the enthalpy of solution can vary between positive and negative. And as we see here, we're likely to have a larger negative or exothermic quantities than we are for the positive endothermic quantities. So examples of the hot and cold packs that we can buy in the drugstore. For hot packs, we can use calcium chloride or magnesium sulfate. And these are exothermic reactions with a large exothermic value, minus 81, minus 91 kilojoules per mole. Cold packs, we can use ammonium nitrate or potassium nitrate, and they have a positive enthalpy of solution, resulting in a cold solution. The concentration of solutions is important. For salt water, saline solution, it can run a wide range. We can have concentrated solutions like a Dead Sea, where the water is concentrated enough that people can float on the water. We use a saline solution as IV solution. We use it as eye drops for moisturizing our eyes. We use it as nose drops. The concentration is different for each one and is designed to be appropriate for each one. If we use the wrong concentration for our IV solution, we can either cause our blood cells or red blood cells to shrivel up or burst. So we have to be able to specify the concentration of a solution in a way that's appropriate, and precise. So we can use qualitative terms, whether solution is concentrated or dilute. Concentrated, we have a large amount of solute for our purposes, and dilute, we have a small amount of solute for our purposes. We have a variety of ways of measuring concentration in quantitative terms. Mass percent would be mass of solute over mass of solution, and this would be this is commonly used for commercial products. Volume percent, volume of solute over volume solution for liquid commercial products. Or we could do mass volume percent. Part per million, part per billion, part per trillion are ways that we measure low concentrations. Molarity is common for chemists. Molality is common for colligative properties. Then mole fraction will be useful for one of our properties. So mass percent, we designate as a percent, mass percent, percent by weight. We use M or W associated with this, mass or weight, to identify a mass percent. And this would be the mass of solute divided by the mass of solution times 100% will equal our mass percent. This is the way that we write it when we're calculating mass percent. If we have mass percent and we're calculating something else, it's usually best to set it up as a ratio. So mass of solute over mass of solution will equal percent of solute over percent of solution, which would be 100%. Now when we are doing these calculations, we have to remember that if we are given the mass of solute and mass of solvent, the solution is the total of the solute and solvent. We have a couple examples on this here. I'll go through one of them. So if we have a nasal spray solution containing 0.65% sodium chloride, we have 45 grams of solution. How much sodium chloride is in there? We can set up as a ratio of sodium chloride, mass of sodium chloride over mass of solution. Maybe percent sodium chloride over percent of solution equals the mass of sodium chloride over mass of solution. We multiply mass of solution across. So we have the mass, 45 grams of solution, times a ratio 0.65 over 100, and that'll give us 0.29 grams of sodium chloride. Part per million, this is useful for dilute solutions. So part per million will be mass of solute divided by mass of solution times 1,000,000. That would be part per million. Or for aqueous solutions, ppm will be milligram of solute per kilograms of solution. This will be for all solutions, so this would be milligram per kilogram, milligram solute per kilogram of solutions. For aqueous, it'd be milligram per liter, since a liter of water is a kilogram of water. So we have a milligram of solute per kilogram of solution is a part per million. ppb, part per billion. For even more dilute solution, it will be mass of solute divided by mass of solution times 1 billion. Or it would be microgram of solute divided by kilogram of solution is part per billion. Molarity, this is what is most commonly used for chemists, because this gives us the moles of the solute, and that's usually what we need for our stoichiometric calculations is moles. So molarity, molar concentration, is symbolized with a capital M, and this would be moles of solute divided by liters of solution. So molarity is moles of solute divided by liters of solution. We can write out that way, capital M equals N divided by V. Or the common way that we might see this is molarity times volume in liters will equal moles. And this is why molarity is so useful to us, because we get moles out of it rather directly. We can use this capital M as the quantity in equations. A capital M is primarily a unit after showing up after a number. But whenever we are doing calculations, such as molarity times volume, we're going to be multiplying this by liters. Well, we'll see that when we change that capital M into moles per liter. Then we see that we want to be multiplying this by liters, and we'll end up with moles. So, let me see here. I have a couple questions here. Let's try this bottom one here. What volume of 8 molar potassium chloride solution is required to make 500 milliliters of a 2 molar solution? Oh, we didn't cover this yet, did we? That's dilution. That's coming up. So let's do this one. 149.1 grams of potassium chloride added up to water to make 1 liter of solution. What's the molarity? So we have to get moles. So we take our grams, we divide it by the molar mass. Grams divided by molar mass gives us 2 moles. We divide it by 1 liter of solution, and we'll get 2 moles per liter, or 2 molarity of potassium chloride. Mole fraction, we're going to need this before the end of the chapter. Mole fraction, we use the Greek letter chi, looks like a capital X, Greek letter chi to represent mole fraction. And mole fraction is going to be the moles of one component divided by the total moles of the whole mixture. So as a fraction, it has no units. Mole fraction has no units. And for each solution, we're going to have at least 2 mole fractions, since we have at least 2 components in a solution. Molality, we'll be using this in this chapter for colligative properties. Molality is a little different in that we're not dividing by solution for this one, we're dividing by solvent. So it's going to be moles of solute divided by kilograms of solvent is molality. For dilute aqueous solutions, this is very close to molarity, since a kilogram of water is a liter of water. So, what do we have here? Let's mention temperature dependence. Molarity has a temperature dependence. Obviously, temperature will not affect the moles of solute, but it can affect the liters of solution. We can have thermal expansion or contraction of a solution. So with the liters changing, potentially changing a small amount, we can have a small temperature dependence to our molarity. Mass percent will be temperature independent, mole fraction is temperature independent, and molality is temperature independent. Molality is represented by the lowercase m.